All right, so we're going to start off by looking at number 9. Where we've got this jet fighter being launched from a carrier with its engines and a catapult. And they tell us some things about the engines and the final kinetic energy, and then they want to know the work done on the jet by the catapult. What they're focusing us in on here is that idea, and probably the first thing that should go into your why, number 9 by the way, is the idea that the net work or the total work done on something goes to just changing its kinetic energy. So I would write it as like the total work done on the plane changes its kinetic energy. That's probably all I would have in my why. If they had, well, maybe I would also should show that work is done by a force through a distance. Just because I know I'm going to end up using the definition of work in my how, so it's good to show that I understand it in my why. If they give me things like what's the speed of the plane or things like that, I might have to show that I understand how kinetic energy is related to speed, but they don't. So that would be my complete. I think that shows all the understanding I need in my why. In my how, I'm going to start off with that same idea, that the net or total work done is the change in kinetic energy. And that's right from here from our equation sheet, W net equals delta KE. So there's two things doing work on this plane. You've got the work of the engines and the work of the catapult, and that's going to equal the KE final minus KE initial. And we're told that it starts from rest, so that's 0 initial. We want to know the work of the catapult, so we're going to keep working the catapult over here, and we'll have KE final minus work of the engine. And we know that KE final and the work of the engine would be the force of the engine through the distance the engine pushes. In my case, the thrust of the engine is 2.1 times 10 to the 5th newtons. So my KE final, I am told, let's see, is 3.9 times 10 to the 7th joules. My force, I just said it and I forgot it already, 2.1 times 10 to the 5th newtons. And I think it got towards X through 90 meters. And a little calculation, and that'll give me the work done by the catapult. Let me know if you need me to look at your individual work on that. All right, so we're going to go on to number 6 here. We've got so we have a 1,000-kilogram car rolling on a horizontal surface with this speed. Right away I'm thinking, okay, inertia and speed, kinetic energy. When it strikes a horizontal coiled spring, if it hits a spring, that spring's going to do work on it. And it's brought to rest in a distance of this. what is the spring constant of the spring? Oh, okay. So here in this one, I'm kind of looking at an energy transformation, is the way I'm thinking of it. I've got this car, it's got kinetic energy. That kinetic energy is going to change because of the net work done on it. And the spring is the thing doing that work. And the way it does work is by storing or releasing potential energy, energy of position. So my thoughts are going to, okay, if the, I've got, this is number 6, I've got the kinetic energy of the car will be changed due to work on it by the spring. The spring will work. I'm going to say work rather than on it. Work done. Oops, that's a done. Done on the spring. The spring will use this work to gain potential energy. So whatever amount of energy the kinetic energy the car has to get rid of is going to directly go to work on the spring, and that spring is going to take that work and use it to gain potential energy. So putting that mathematically, the change in kinetic energy of the car is going to equal the work it does on the, and that work is going to equal the potential energy gained of the spring. Just summing that all up mathematically. And then I need to remember from my equation sheet that kinetic energy is related to your inertia and your speed, and the potential energy stored up by or gained by the spring is going to be due to its spring constant and how far it compresses. All right. Now I could do the intermediate step in there with my F and D. I'm going to skip this central work idea, realizing that with an this equality I can just go right over it. So the kinetic energy of the car is going to go from kinetic energy final minus kinetic energy initial, and that's going to equal, it should actually say delta PE of the spring. That's going to equal PE final of the spring minus PE initial, and this is a car. The final KE of the car is going to be 0 because it's going to come to rest. The initial tension of the spring is going to be 0. It's going to come to rest. If you look, I have this kind of interesting negative and positive relationship here, where I have negative kinetic energy of the car, initial of the car, equals the, whoops, I left off a letter there. The potential energy here, final of the spring. And the reason that I have that negative relationship is it's doing this, it's taking energy away from the car, so it's losing energy, but the spring is gaining energy. Remember, these aren't vectors, so there's no directionality here, but it's that opposite relationship, just like left and right, where the car is losing energy and the spring is gaining that energy. So I'm actually just going to completely forget about that negative sign and not worry about it, because now I understand the gaining and the losing. So for my kinetic energy, I have 1/2 inertia of the car, speed of the car squared. For the potential of the spring, I have 1/2 spring constant, um, x squared. I know all those values, but I should make sure that I use base units. So like my inertia is in kilograms, yay, I don't have to convert it, but my speed is given to me in kilometers an hour. I need to make sure I use meters per second, not kilometers an hour. And then my distance is in meters, so that's all happy, because they want this in Newton meters. So, what was mine, 45 kilometers an hour? Yeah. I'm just going to use the tools in my calculator to convert that 45. You can, of course, always do that. You can even do it using Google, right? You can type in 45 kilometers an hour and ask it to go into meters per second. I get 12.5 for mine. So I'm going to substitute in 1/2 minus 1,000 kilograms. Yes, 1,000 kilograms. 12.5 meters per second squared. Probably the most common math mistake is to drop that squared. 1/2 K, which I'm looking for, and my compression is 2.2 meters. And that again is squared. Don't drop either of those squares or you won't be happy. And then it's just math after that. So let me know if you need help individually on your solution. And then we'll get to number 8 in a minute or two. Or number 10, depending on how the votes go. Alright, so we're moving on to number 8. And the human body could convert a candy bar directly into work. How high could an 82-kilogram man climb a ladder fueled by 1 bar? Now, when we went through the example problems, this one was called Candy Mountain, I think, or something like that, or Candy Mountain Climb. They do add the wrinkle in here that if he jumped off the ladder, what would be his speed when he reaches the bottom? So what we're looking at here really is 2 conversions. We're looking at, so he takes the energy from the bar and does work on himself to change the amount of potential energy gravitationally he has. And then after he has changed that gravitational potential energy by changing his position, he then changes his position again by jumping off the ladder. And so as he goes down, gravity does work on him to change that gravitational potential energy into kinetic energy as his position changes again. So what I would go with here is that probably I'd start with that first transformation. The energy from the candy does work to change his potential energy gravitationally. And then I'd probably gap a little bit and say, on his way down, his weight does work to change his PE grav to kinetic energy. realizing one of the big understandings here is anytime we want to change the amount of energy someone has, we need to do work on them. And that work always causes the energy to change. So, in this one, let's start off with do they label them A and B? Yes. So in part A, the work done by the candy bar, call that work CB, must equal his change in potential energy gravitationally. So work CB equals PE final grav minus PE initial grav, and we're going to call that potential energy at the bottom 0. Remember, just like when we were dealing with kinematics, 0 is where you place it. All right, so we can say at the bottom of the ladder, we're going to call that the 0 point. You could also say the top of the ladder was 0 if we really wanted to. But I think it makes more sense to do it at the bottom here. They tell me my work by the candy bar, 14,000 kilojoules. So that's, 1,400 kilojoules. So that's 1,400 times 10 to the third joules. PE, sorry, I should have written that equation before. PE grav is his weight, mg, times the height. So that would be his weight times the height. His mass is 82 kilograms. Gravitational field on Earth is 9.8 newtons per kilogram, and h is what we're looking for, the height that he can climb the ladder to. Then we go on to part B, and in part B, on his way down, his weight will do work to change his potential energy gravitational to kinetic energy. So again, he has potential energy gravitational because of his position. Work's going to be done on that and change it into kinetic energy. His potential energy gravitational will be mgh. His kinetic energy will be 1/2 mv squared. Sorry, this should be changed and changed. And again, we would end up with that negative sign thing, realizing it's taking it from one form to the other. Anything cancel out there? The m's. So does it matter how much mass something has when it falls? No. There's another proof of what we saw for a long time. So now it's just substitution. You know G, you know H because you solved for it right above. You know 1/2 because you're smart. And then you're looking for B that you want. And you'll end up with it in meters per second. What I believe they asked for it in. Let me know if you need me to look at your individual work on that one. I'm glad to come over and look.